Page 7. Good. So first of all, when I look at this function, I will definitely immediately factor it. Here I didn't have to do that. It only contained one factor at the top, one factor at the denominator. But this is a more sophisticated rational function, so I have to do that. Okay. Can anyone give us the factored form of the top? Anyone? Well, so it's x plus 2, x minus 1. So it's x squared minus x plus 2x minus 2. The denominator, I factor out a 2, and then I have x squared minus 1, which will be x plus 1, x minus 1. I need the factored form for many reasons. For the x-intercepts, for the domain, for limits, for a lot of other things. I will get my table going. I don't need this page anymore here. When you finish filling up the table, then you know you're done and you're ready to graph. Can anyone give us the domain of this function? Anyone? Well, x cannot be 1 or negative 1. So if the function is undefined, of course, its derivatives will be undefined. At that point, after I state the domain, you don't have to write it on the side. If you're using a table, which you have to, I understand what you're doing. So it's very clear to me that you don't have to write it on the side what the domain is. You already specified it by presenting the table. At this point, I'm allowed to simplify. So the simplified form will be this. See what happens? The factor of x minus 1 disappeared. So x equals 1 is not a vertical asymptote. It didn't stay in the final form. It's a whole. That's why thank you for choosing it. So I can cross this out from my list anyway. But the factor of x plus 1 stays, so x equals negative 1 indeed is a vertical asymptote. The hole in the graph is given by the fact that the function is undefined at 1, but the factor disappears, which clearly states that that cannot be a vertical asymptote anymore. Good. At this point, I will plug in 0. So 2, this is 1. 2 over 2 will be 1 for f of 0. I also have to determine when y is 0, x plus 2 over twice x plus 1 is 0. A fraction is 0 only when the top is 0, which means negative 2 comma 0. Now I have to determine these limits. A lot. 6 different limits. And then I'm done with the function. And I can move on to the first derivative. Okay, the limit as x approaches negative infinity from x plus 2 over 2x plus 1. Then the other one right here, limit as x approaches infinity from x plus 2 over 2x plus 1. Can anyone tell us these limits? Give us these limits.
wouldn't it be just 1 over 0 times 1? Is that?
Okay, let's do this. So it's infinity over infinity. Doesn't matter. The sign is not important. So this is limit. I differentiate the top and I get 1.
Right.
I differentiate the denominator and I get 2. So the limit is 1/2 in both cases, which means y equals 1/2 is the horizontal asymptote. 1/2, y equals 1/2 HA. 1/2. Is this clear now?
Yes.
Perfect, thank you. Okay. Then, limit as x approaches -1 from the left, and limit as x approaches -1 from the right, from x plus 2 over twice x plus 1. X plus 2 twice x plus 1. Okay. The top is positive. The denominator, however, is 0. So I will plug in -1.1. -1.1 plus 1 is negative. The top is positive, negative. -1.1 from the right, which is -0.9. This is positive, this is positive, positive. Which absolutely means that x equals -1 is a VA, as we knew already. Finally, we have, so I have negative on this side, and I have positive on this side. Okay, finally, the limit as x approaches 1 from the left, from x plus 2 over twice x plus 1, and the same thing with 1 from the right, from the same function, of course. So 1 from the right or left, they have to be the same, it doesn't matter. So 1 plus 2 is 3, and 1 plus 1 is 2, 2 times 2 is 4. Which means 1, comma 3/4 holding the graph. So the limits, both sides, 3 over 4. Look how much work just for the function. Now finally the derivative. I shouldn't say finally because there is a second derivative after that. So f prime. You know me, I'm not going to involve 1/2. It can wait patiently. The top prime is 1, so the denominator minus the top times the denominator prime, which is 1 over x plus 1 squared. Okay, so 1/2 x plus 1 squared, x plus 1 minus x minus 2. Okay, nice. The top is -1. The denominator is 2 x plus 1 squared. Nice. Never 0. No critical numbers. Which means I still need the sign. So what is the sign of this expression no matter what? And I will put it in.
Isn't it positive?
Yes,
Negative.
it's always positive, but
It's negative.
always negative. Moment of truth. That's when I catch my mistakes, right here, right now. When I say, oops, they don't match, they don't work together. Okay, let's see. 1/2 goes down to 0. Yes. From 0 down to -infinity. Yes. From infinity down to 1. Yes. From 1 down to 3/4. Yes. From 3/4 down to 1/2. Yes. Ah, good. Now I need a second derivative. And the second derivative, the first derivative for me is this. So then the second derivative will become, I bring down 2. It will destroy the whole thing. So I just have x plus 1 to -3. because it's -1/2 times -2, which is 1. So this is 1 over x plus 1 to the third. Okay, so I need to study the sign. It's never 0. No IPs. So to the left-hand side of -1, I'm going to plug in -10. -10 plus 1, negative. In the middle, I'm going to plug in 0, positive. On the right-hand side, I'm going to plug in 10. Okay? Does not hold water, and it does. I'm ready to graph. Nothing else matters but the table. I'm not going to look anywhere. All my information is right there in front of me. When I graph a function with asymptotes, I must start by graphing the asymptotes. And here they are. 1/2. Y equals 1/2. And -1. For x, of course, x equals -1. And 1, comma, 3/4. A hole in the graph. Okay, opening down. Let me also put the -2 here, -2, 0, and 0, 1. Okay, ready? So the table says, come from 1/2, cross at -2, 0, and go to -infinity. No problem. Then on the other side says, come from positive infinity, cross the y-axis at 0, 1, go through this open point and approach 1/2. No problem. And this was x squared plus x minus 2 over 2x squared minus 2. Now, if I want to find the range, be very careful here. Yes, 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 yes. So -infinity, 1/2 union. Yes, 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 no. Yes, yes, yes. So 1/2 to 3/4 union 3/4 to infinity. There is a hole right here. And there is another hole here. So the graph has 2 holes basically, but you know what I mean. Just this one is an open point. Very good problem. Thank you so much for choosing it. I would have looked for one and maybe not find this one this nice. Thank you. You earned your privilege to choose again. I'm kidding. Everyone can choose. Okay, I would like to talk about the slant asymptote and give an example for that and move on. The rational functions with a slant asymptote. Rational functions with slant asymptote. They are a very special category. Only when the numerator has degree, the denominator has degree n, and the numerator has degree n plus 1. This is the only kind that has slant asymptote, but not horizontal asymptote. If it has a slant, it cannot have horizontal. Okay. Ready? So what would this really mean? Degree 3, degree 2. Degree 10, degree 9. degree 7, degree 6. That's what it means. These are the only ones that have slant asymptotes. And I'm trying to find here one that is nice, but I'm not capable of finding one that is nice. So I'm going, let's look at 54. So the function is f of x equals x to the third over x squared minus 1. So what does the slant asymptote mean? It's not horizontal. It's slant. Either like this or like this. And of course, the function, like with the horizontal, will follow the asymptote eventually. So this time, if the function has a slant asymptote, the function will follow the asymptote at infinities, like it would for a horizontal. That's the only difference. It's not horizontal, it's oblique, either this way or this way, which makes the function approaching infinities now, not a number. Infinity, not a number. That's the only difference. Everything else is the same. Okay, so here is a function like that, degree 3 and degree 2. So the numerator has degree 1 unit higher than the degree of the denominator. Okay, I'm going to start my table. I will immediately factor the denominator for domain and for other things. And then we'll look at the function and then the derivatives and graph it. So f prime of x, f of x in the middle. You can change the order, you can do whatever works for you. So I see that the function is not defined at -1 and 1. And if the function is not defined, its derivatives will not be defined either. Good. So when x is 0, y is 0, and there is no other x-intercept, I have to determine these. The factors in the denominator do not go away, so I know that these must be VAs. There is no discussion there. And that's it. So then after I determine these 6 limits, then I can move on to the first derivative. Okay, so limit from x to the third over x squared minus 1 when x approaches infinity, and then limit as x approaches negative infinity from x cubed over x squared minus 1. So the numerator goes to infinity, the denominator goes to infinity, so I can use L'Hopital's rule. So this is limit as x approaches infinity from 3x squared over 2x. I will simplify by an x, and when x approaches infinity, this is infinity. In the same way, I will get the same thing, but this one, when I approaches negative infinity, will be negative infinity. So when x approaches infinity is infinity, and here is negative infinity. Now limit as x approaches -1 from the left of x cubed over, and I prefer to write x plus 1, x minus 1. It's easier to determine the limit. And limit as x approaches -1 from the right from x cubed over x plus 1, x minus 1. Let's see what we get. So the numerator is negative in both cases. And now -1 from the left, -1.1, negative, negative. So 3 negatives. -1 is from -0.9, but this will be positive, and this will be negative. The top is negative, so positive infinity. So we know that this is a vertical asymptote. So we have negative infinity and positive infinity. And finally, the limits around 1. So limit from x cubed over x plus 1, x minus 1, when x approaches 1 from the left, and finally when x approaches 1 from the right. And let's see what we get. So the top is positive in both cases. 1 from the left means 0.9. This will be negative. And 1 from the right, everything is positive. So negative infinity, positive infinity. And obviously x equals 1 is a VA, which we knew. Okay, that is done. The first derivative now. Ugly situation. Of course, I'm going to use this. Let's see what we do with this. So this is 3x squared and x squared minus 1 minus x cubed times 2x over x squared minus 1 squared. And yes, of course, I would factor out x squared. I refuse to not simplify by factoring. Okay, then, so what we have here is 3 distributed, so 3x squared minus 3. I took out x squared, so this is minus 2x squared. So 3x squared minus 2x squared is x squared. So x squared minus 3 over x squared minus 1 squared. This is very ugly because I'm going to get into the same situation. I'm pretty sure I didn't leave enough room. I wouldn't be able to anticipate that. So x equals the square root of 3 and x equals negative the square root of 3. And who knows what the second derivative will come up with. Okay. So it's 0 here. And the square root of 3 and negative the square root of 3. Studying the sign now. But that is not ugly. Because this is always positive, I'm not going to spend my time on it. And this is only positive, I'm not going to spend my time on it. So the sign is given by x squared minus 3. So here, like negative 10, that would be positive. 0, that would be negative. And outside will be positive. Moment of truth. I have to find this number, and I have to find this number. Very ugly. I'm going to use the calculator to plug in this function, the square root of negative 3. The function is odd, so these will be opposites. So in y equals, I plug in x cubed. Be very careful with parentheses in the denominator. That's very important. So x squared minus 1. And then second and table. And I want the square root of 3. Square root of 3. And I get 2.59, 2.6. If this is 2.6, this must be negative 2.6. Because the function is odd. Or you can check by plugging in that. Okay. So now this is my moment of truth. This is when I say, well, is this okay or not? Okay, so let's do that.